For number 8, we have two concentric circular wire loops of radii R1 is equal to 23 centimeters, R2 equal to 35.5 centimeters, are located in an XY plane. Each carries a clockwise current of 9.52 amps. For part A, we're asked to find the magnitude of the net magnetic dipole movement of the system. We have our I is equal to 9.52 amps, our R1 right here equaling 23 centimeters, and our R2 equaling 35.5 centimeters. To find the magnitude of the net magnetic dipole moment, we are going to have to use this formula. We have the magnitude equal to the number of terms in the wire times the current of the wire times the area of the wire. Since we have two radii, we have two loops, two separate loops, we are going to have a magnitude net equals to n for the first loop, n1, times the current of the first loop times the area of the first loop, plus number for the second loop times the I of the second loop times the area of the second loop. And these are being added together because they are both going in the same direction. We can highlight this because it's important to this problem currently. Our number of terms isn't stated here, so we can assume that it is just 1 for both of these. Our current is the same at 9.52 amps, and the area is the only thing that is going to be different. We can factor our n and our i's out because those are both the same, and we'll write this as n times I times the area of 1 plus the area of 2. And the area for a circle is just A is equal to pi r squared. So now that we know all this information, we can start plugging in our values. Our n is just 1 and our I is 9.52 amps, so we're plugging this in here. We can factor out a pi since these both are going to have it, and since it's area, it's going to be in meters, so we have a pi meters. And then inside of here we have our radiuses squared, so we have 0.23 meters plus 0.35, and then we have actually 0.355, and we already have the meters out front, so we don't need it inside of our parenthesis. And both of these are going to be squared separately like this. We also need to square our meters in here because it is part of the radius. And after we plug everything into our calculator, we are going to get the magnitude net equaling approximately 5.35 amps times meters squared. That is our work for part A. Now we are going to look to part B. And in part B we have the same problem. However, the one difference is that the current in our inner loop is going to be reversed. So instead of going this way, it's going this way. For B, it's practically the same thing, except the difference is the reversed current in the inner loop. So in our inner loop, in here, our current is now going to go this way, while our outside current stays the same and goes this way. And now that these are going in different directions, instead of adding here, we can change this to not add but subtract, since they are going in different directions. So they are now being subtracted from one another. We can look at the same work where we copy all of this and just change the sign on the inside. So in here we're going to get rid of our positive, and in here we're also going to get rid of our positive. Now that we have a different value in our parentheses, we can plug this into our calculator, and we get approximately negative 2.2 amps per meters squared. The negative is just the direction. It's basically saying that it will be going in this direction. There's more current flowing in this direction because of the radius, and since it's just direction, we don't need that in our answer, and we can write our final answer as being approximately 2.2 amps per meter squared, or amps times meters squared. And that is all the work for number 8.